I would love to show you this classic video in its entirety, but just to avoid any form of copyright infringement, I'll just include a link somewhere up above or down below. Anyways, it's a great video that's made over 50 years ago, and it describes really well the differences between uniform motion and uniform acceleration. All right, so please watch that when you have the chance. In summary, what the video describes about is these two different frames of reference, all right? An inertial frame of reference and a non-inertial frame of reference. An inertial frame of reference is one which abides by Newton's first two laws. What does it simply mean? That you're traveling at a constant velocity, even if the value is at zero, all right? Suppose you're here on Earth right now and you're, playing catch with a friend, all right? You toss the ball and your friend catches it, and they toss the ball and you catch it, and you don't notice anything funky going on. Everything just behaves as the way it should. And that's because you're here on Earth, and we'll take it that, at least from our point of view, the Earth appears stationary. All right. Well, it is moving, but it's moving so slowly in comparison to, in the event of everything else. All right. What I mean by that is that it takes 24 hours for the Earth to orbit a complete cycle, and your activity has probably ended well before 24 hours. So you really don't notice the outcome of the Earth, and you'll take that as an inertial frame of reference. All right, because you appear to be stationary. Interestingly, if you do the same experiment while you're on an airplane or on a cruise ship or even in the subway, as long as it's traveling at a constant velocity or at a constant speed in a straight line, you can toss that game of catch and you won't see any difference in it. It'll still be a parabolic motion between player A and player B. However, if the train suddenly speeds up or suddenly comes to a stop, or if it takes a turn or curves upwards for any reason, then yes, the trajectory of the ball will completely change. In that case over there, you're in a non-inertial frame of reference or in an accelerated frame of reference. And that's what we'll be talking about in today's lesson. Okay. And before we move on, I just want you to think about something, because this will help us understand these other terms. All right. Let's say that, you call shotgun on a car and your friend suddenly begins to accelerate the car. Your body gets stuck against the seat as your friend accelerates. As your friend slams on the brakes, your body ends up moving forwards. And here's the question. Is there really any force grabbing your body and pushing against the seat when your friend's accelerating? Or is there any force that's pushing you against the seatbelt as you're decelerating? Truth is, there is nothing. It's just inertia doing its job. Remember that inertia is a tendency for an object to maintain its same state of motion. So objects at rest tend to stay at rest, and objects that are in motion will still move in a straight line at a constant speed. That's what inertia is. All right. So when you're going around a turn, all right, and if you're in a car and your friend's trying a huge turn, you'll notice that you end up slamming against the edge of the car. And it's not that your body is naturally wanting to move against the car, it's the car trying to maintain you in that circular orbit. All right. And that's known as your centripetal force. So centripetal force is the force that allows you to maintain that orbit. Otherwise, inertia will kick in. All right. As your friend's driving straight forwards, your body's still moving forwards. So as your friend takes a turn, your body continues to move forwards, but it's the seat belt or the side door that's pushing you, preventing you from going forwards. Instead, you start turning. All right, and that's what centripetal acceleration is. You're constantly turning around, and there's this force that makes you go to the center of rotation. That's different than something that's known as centrifugal force. Centrifugal force is what you perceive in your head. It's not a real force at all. All right, if you recall back this ride that we talked about in an earlier episode, I think it's episode 8, if you go into this UFO spaceship and the operator says, okay, let's start, rock and rolling, and they start blasting the music, suddenly you feel like your body is being pressed against the wall, like something has gripped you, forced you against the wall. That illusion is known as a centrifugal force. All right, so your perception of something grabbing you, pushing against the wall is a centrifugal force, but in truth, it's the centripetal force that allows you to stay in the ride. Otherwise, the ride suddenly disappears. You're just traveling in a straight line afterwards. In fact, we apply the centripetal force, or not we, a video game applies it, and it's the game of Halo. I'll include a card somewhere up above or a link down below so you can watch that video as well. All right, and yeah, the whole game is under the premise that it's the centripetal force or the centrifugal force that allows you to stay in that planet called a halo. Hopefully I didn't spoil anything in the game if you haven't played it yet. All right. So the centripetal force is the force that allows you to maintain that circular orbit. And let's go and derive out these equations. Okay? All right. So we know that the centripetal force is equal to mass times centripetal acceleration. This comes from the formula of F net is equal to ma, except in this case over here, your F net is your centripetal force. All right. So we can take the equations we covered in our last lesson and just simply sub it into equation 1. So if we sub equation 2 into equation 1, we get Fc is equal to mv squared over r. If we sub equation 3 into equation 1, then we get this formula over here. And if we sub equation 4 into equation 1, we end up getting an equation that looks like this. Now the first 3 equations, that will be given to you on any future quiz, test, or exam. However, for these ones over here, I hope you can do the quick substitution because they won't be provided for you. All right, you'll need to be able to sub one into the next to create these next extended equations. Okay, so these are the equations to find out the net force required for you to maintain orbit, provided they're given the speed as well as the radius over orbit. All right, so you're traveling a constant speed around it. Or if you're given the period, or how long it takes for you to make a complete circle, if that's given to you, you use this equation over here. And if you're just told that you go around the loop 5 times a second, then yes, you'll want to use the third equation for that case over there. Okay, so let's get on to the fun stuff. Let's do some calculations, starting off with our control calculation. A plane that's traveling at a constant velocity or a constant speed in the same direction. All right, how does that impact us in the feeling of what we get when we're in the seat of the plane? When we draw the free body diagram, if I have that here, oh, naughty me, let's draw that out. Okay. All right. So if you're sitting in the plane, it's the lift of the plane or the normal force of the seat acting on you, which is called the lift of the wings, because we're going to box in the whole plane right now. Okay. It's the lift of the wings that allow the plane to remain afloat. And yes, the force of gravity is pulling it down. Okay. So that's our free body diagram. There you go. Always include a coordinate system so the reader knows what you're defining as up as well as forwards. Okay. And again, if you're traveling at a constant speed at the same altitude above the Earth's surface, then your F net y will go to 0. If that's the case, then the lift force and the force of gravity have to match dollar for dollar. That's how you're able to travel in a straight line. Okay, and if Fg is equal to mg, then your F lift is equal to mg. Suppose you have a 1 metric ton airplane and it's traveling at a constant velocity, then the normal force, or the lift force in this case over here, is equal to 9.8 kilonewtons. Done. That's our control value. All right, and we're going to do everything else based upon this now. Okay, so let's say that you're not traveling in a straight line anymore, but now you're going through a loop-de-loop. And the forces acting on you will change in every circumstance. So if you're accelerating downwards, it'll be different than you at the bottom of your rotation, which will be different than you being at the top of your orbit. Okay, so we're going to start off with a case where you're at the bottom of the loop-de-loop. Okay, what is actually happening at that state over there? Okay, and yes, you will suddenly feel quite a bit heavier as you loop at the bottom. If you've ever been on a roller coaster ride, you might notice that. As you go to on top of the loop, you suddenly feel a little bit lighter, and then you feel a whole lot heavier when you're at the bottom. Okay, the smiley face is just so that we understand what our frame of reference is. Okay, because from here, we're taking it that anytime that you are moving towards the center of orbit as the positive direction of travel. That's how we define it. Okay, so even the free body diagram is right over here, our definition of positive is always to the center of rotation. All right, so our other forces are our lift forces and our gravitational force. Okay, so let's go and calculate out everything else now. All right, so our F net in this case over here, if we take it that towards the center is positive, is equal to the lift force of the wings subtract the force of gravity, which is pointing downwards. Okay, and our F net is the net force that allows us to orbit around. So it's F net C, if you see there's a little C over there. Okay, if you flip back to the previous PowerPoint slide, we have 3 formulas that we can use. If we're given V and R, then we probably want to use the one of F net C is equal to mv squared over r. And I believe that's what I used right over here. Okay, we just plug it right in. All right, we have all the numbers up above. Go ahead, pause the video, unpause, and I hope that it matches up with this in your answers. Okay, remember our previous value was 9.8, I think, kilonewtons, and now our value is 19.6 kilonewtons. All right, so it's effectively doubled here. In fact, we can do a side calculation to figure out, how much this has changed us in the perception of g forces. Okay, by definition, a g-force is just a multiplier compared to the force of gravity here on Earth. So right now, as you're seated at your seat watching this video, you're experiencing g-force of just 1g, or 9.81 newtons per kilogram. All right, but there are other events, especially if you're going around in orbit, your g-forces either increase or decrease. All right, and that happens anytime you're in a non-inertial frame of reference or you're in an accelerated frame of reference. All right, the g-forces do change at the end. So we look at our calculations over here. First off, we need to convert this into an acceleration. Acceleration is equal to F net over mass. So we take our 1.96 times 10 to the 4 newtons, we divide it by 1,000 kilograms, then we take that calculation and sub it right into here. Unpause if you've paused, and you'll find out that in this case over here, we get a g value of 2 g's. Why is it 2 g's? Because I calculated that way on purpose. All right. So with a speed of 108 kilometers per hour as you're going around the loop, okay, so you're maintaining that speed all the way around. When you're at the bottom of the loop, you're experiencing as much as 2 g's. Okay, and it will change as you're going around the loop. So we're only going to deal with extremes in this unit. So we're going to deal with, what happens when you're at the bottom of the loop and what happens when you're at the top of the loop. Okay, so let's bring this plane to the top of the loop. In this case over here, the lift force of the wings will still be pointing downwards. That's our FL. All right. However, our gravity is also pointing downwards as well, because we're taking everything from the frame of reference of the center. Okay, that is defined as our positive direction of travel. Oh, I have it animated in the lovely smiley face, as well as the lift force. Okay, so when we draw our free body diagram now, this time around we're defining downwards as positive. Okay, and we have two downward forces. We have our lift force and we have our gravitational force. Remember, with all force problems, you always need to start off with a free body diagram. All right, so this is our diagram for the plane, at least when it's at the top of its orbit. Okay, in this case over here, we know that our F net is equal to two positive values. So it's equal to positive FL plus positive FG. Again, we don't worry about the minus signs because it's already somewhat been factored in our calculations. We're taking that downwards as positive. Okay. All right, so our net force is equal to the sum of these two forces here. And given M and V and R, we probably still want to use F net C is equal to M times V squared over R. Sub that in. Oh, maybe I'll just write it out here on the side. Okay, this is equal to mv squared over r. Right? Isolate for FL, pause, unpause, and I hope that you end up getting this calculation over here. Yep, you're experiencing free fall, at least at the speed over here. All right, so this is the speed that I pre-calculated out earlier on. Don't forget to convert that. All right, 108 kilometers per hour, you need to divide that by 3.6 to get it to a measurement in meters per second. So if you didn't get 0 newtons, maybe you want to check that out. Okay, and then go through all the calculations. So I chose that number because I knew that number would work out beautifully in this case over here. All right, that you'll be experiencing free fall at least at that speed. Now, if you increase the speed, which is what they naturally do as, in roller coaster rides, because they never want you to experience 0 G's at the top, all right, it'll be a higher number. So go ahead, plug in something like 120 kilometers per hour, convert that to meters per second, and you'll find out that your lift forces, it won't be at 0, it'll be some numerical value. All right, that way you still stay seated on your ride. All right, and if you don't go as fast as that, let's say you drop down to 100 kilometers per hour and you do your calculations, you'll notice that you end up getting some sort of negative answer. All right, what does that mean? Well, that means that the lift of the plane doesn't really help you out anymore. All right, because you'll start to fall right off the plane. So hopefully you're wearing a seatbelt in this case over here, if you're not flying fast enough. Okay, that's about all for now. Make sure you do all your homework, check your answers, and I'll catch you in the next episode. Bye now.